Hi everyone, Mrs. Basega here, and today we're going to learn how to calculate the friction force. Now, as you recall from last Wednesday's video, we used a applied force versus friction force graph and got three distinct regions. The static region, in which the friction force was always equal to the applied force, and this was because this was at static equilibrium. Think of it like this. If I put an applied force to the right, and it was not balanced by the friction force to the left, then it would accelerate. These have to be balanced because they're in equilibrium, guys. But if I put too much force on it at that threshold of motion, if my applied force is large enough, then all of a sudden it starts to move. The threshold of motion is the maximum applied force that you can put on this system in order to start or in order to get it out of static equilibrium. Symbolically for that, we write that as F sub friction static max, and this is where it switches to moving or kinetic friction. Keywords to look for the threshold of motion would be start moving. Finally, the last region is the kinetic region. I've heard people call this kinetic energy, and guys, you want to avoid that. Kinetic simply means moving. This is the constant amount of friction that two solid surfaces feel as they slide past one another. As long as they're moving at any velocity relative to each other, that constant value of kinetic friction stays the same. So static, threshold, and kinetic are three distinct regions of this graph. And so what we're going to do is we're going to write one big piecewise function. It looks something like this. For static equilibrium, the friction force is equal to the applied force. At the threshold of motion, the maximum static friction force is equal to mu, the coefficient of friction, times the normal force. I'm going to use TOM as my abbreviation for threshold of motion. Finally, that friction force kinetic is equal to coefficient times normal, but we just select the kinetic coefficient instead of static. These three equations together give the one piecewise function that works for friction force. When you're given a word problem, you just have to figure out which part to use then. In this case, this is a child sliding to first base. If they are sliding, that is kinetic friction, so I would use the kinetic friction part of that equation. Notice that I need the normal force, and you can make the assumption that in this case, the child sliding as a result of friction or sliding in baseball is going to have a normal force equal to gravity. So I'm going to take the coefficient of friction of 0.8 times 30 newtons of normal force, and that'll give me 24 newtons of friction force. If I draw this back on the free body diagram, we see that there's a friction force to the left, and the child's not doing any applied force to the right. Like they aren't shimmying themselves across, they're just sliding. So that negative acceleration in this case is because there's one friction force with no applied force, and so it's accelerating to the left or slowing down. You will be expected to make this friction graph on your own though, so let's show you how to do that. Let's say we're in a lab and we are pulling a 20 Newton weight across the surface. Notice that the weight is equal to the normal force that I need in order to solve this static friction equation. By solving the static one, I can figure out where the threshold of motion is. I'm plugging in 20 newtons for the weight, the static coefficient of 0.6, and I see that the static friction maxes out at 12 newtons. So I'm going to put a point at 12, 12. 12 newtons of applied force gives 12 newtons of friction, and everything earlier than that, lower applied force than that, that is the static region. Dude, last step already. Calculate the kinetic friction force, and that'll give us that horizontal bar. The kinetic friction force at 8 newtons corresponds to 8 newtons on the y-axis. So no matter what, as long as this is moving, the kinetic friction force is 8 newtons. I need to apply at least 12 newtons to start it moving, but as soon as I start it moving, it drops down to 8 newtons of kinetic friction. Now let's do a related problem. So this is the same problem, just continuing on to the next page. The normal force was 20 newtons. That means I can calculate the mass of this object. I'm going to need that in order to find the acceleration. So dividing by 9.8, I get a mass of 2.04 kilograms. Now what about this question? If I apply an 18 Newton force, does it move? Well, yeah, I needed 12 newtons to overcome the threshold of motion, so 18 newtons is in the kinetic region, right? Okay, so it says I have 18 newtons applied force. So in my free body diagram, there's 18 newtons to the right, minus 8 newtons of friction, and that gives me a net force of 10. Finally, calculating acceleration, 10 newtons of net force over 2.04 kilograms gives me about 5 meters per second squared of acceleration. Because there's more applied force than kinetic friction force, it's accelerating, and it's positive because it's moving to the right. So sometimes you'll see people shorten the friction equation to just look like friction is equal to coefficient times normal. But we can use this to help think back to what this means qualitatively. If I wanted to make friction lower, then I just need to lower either of those two variables. I could change the coefficient by adding oil or smoothing the surface or changing the surface. But I can do lots of things to normal force. I could lower the normal force by bringing it to the moon, right? Less weight, less normal force. I could put it on an air hockey table. If the surfaces don't touch, the normal force goes to 0. We're going to focus on this lift up at an angle, though ramps and elevators would also be able to lower the normal force. If we do this lift up at an angle one, which I'm trying to highlight here in red, we can review two-dimensional forces. So let's close out by thinking about this normal force, friction force, angle relationship. If I just have a box that I'm pushing horizontally across a surface, gravity is equal to normal force and friction is equal to mu times normal force. So the friction force feels like it normally would. I could make this easier on myself though by taking my same applied force with my same weight and applying it up at an angle. That's because if I'm pulling upward, that makes the normal force smaller. Lifting up lowers the normal force and lowers the friction force. So it tends to be easier to move an object if you lift it up on an angle. Which means if I do something like push down at an angle, that same applied force but downward at an angle has a negative y component that the normal force has to go cancel out. And as a result, normal is larger than gravity. This makes it harder to move. When you push down, that makes the normal force larger, meaning more friction that you have to work against, making it harder for this object to move. So we're going to try all these problems in today's practice. Best of luck.